Okay, good. So the topic of this last one is bottom-up thermalization. So this is kind of the question here is, now that we have this plasma field configuration in the initial stages of a heavy ion collision, we have collided the two nuclei. We have gone to times order 1 over QS, like 0.1 Fermi, 0.2 Fermi in time. The question is, how do we go from here to a quark gluon plasma, or at least a gluon plasma? Okay, so quark, I'm not going to talk about quarks here at all, but the question is gluon plasma. And the question now here, of course, there are many people studying this from different points of view. Some people say that it should be done with ADS-CFT and extremely strong coupling. But now that here, as a theoretical question, one can ask, how does this procedure happen in the extreme weak coupling? In the extreme weak coupling limit, and this was a alpha S very, very, very much smaller one. Okay, and this was a question that was first addressed by Bayer, Miller, Schiff, and Son a little bit more than 20 years ago. Then there was a huge explosion of discussions about plasma instabilities and whatever, and lots of work done. And in the end, I think the relatively general consensus is that I think probably BMSs were right after all this discussion. It's actually a relatively readable paper. It has equation. It doesn't have an equation with a proper equal sign. It only has equations with proportional to, because we are really looking at the very extremely weak coupling. So the starting point to set up our physical system is that coupling is very weak. We have a hard scale, which is now our QS. So we have a system of gluons that have transverse momenta of the order of this QS, which we consider to be a very, very hard scale, hard enough form. This is the hard scale in the problem. Okay. And then we will later then talk about the soft scale, which is the Debye scale, which is could be less than QS, maybe a lot less, maybe not that much less, but at least much less than QS, so that we have a scale separation between Debye scale and QS. And then we start our system at QS tau of the order of 1. We start our system in an overoccupied state where, and this symbol will appear a lot in this. This is the particle phase-space distribution of particles. So this F is the density of particles in space, three-dimensional space, and three-dimensional moment. So this is the thing that appears in kinetic theory. If you do kinetic theory, where particles have some distribution in phase space, and they collide with each other and interact. And then this is the connection between between somehow very off equilibrium particles that can be described in kinetic theory, and then a hydrodynamical description which can be achieved as a limit of kinetic theory when you're looking at systems that interact strongly enough to be equilibrium. So we will be using the language of kinetic theory, where this particle number distribution is kind of characterizes our system. So we start off with a system where this is very, very much strongly overoccupied, so 1 over alpha S. So whereas in a thermal equilibrium, F would be of the order of 1. Right? In the thermal equilibrium, F is the Bose-Einstein or Fermi-Dirac distribution, and there's no weak coupling in the Bose-Einstein. Well, in this case, we're talking about gluons or bosons, so there's, you know what the Bose-Einstein distribution is. There's no coupling constant in the Bose-Einstein distribution. It's just numbers of order 1. Okay, so this is our initial condition, and then we have a boost invariant expansion. Expansion. And the boost invariant expansion means that in our initial state, typical Z components of momenta of particles are much less than transverse momenta. And the transverse momenta are the ones that are of your QS. So one can think of this boost invariance in two ways. If you think about it in the field theory language, the system, because the system field configurations are boost invariant, so the system is expanding in the longitudinal direction with the speed of light, and your fields are independent of rapidity. This means that all the z components of momenta are redshifted. System is expanding, so momenta are redshifted. So they become small. If you think in terms of a kinetic theory description, what you do is that you take this expanding system and you look at a fixed box of fixed size in z, and you look at this box, and you wait for some time. All the particles that have momentum in the z direction, they fly away from your box, and because the system is expanding, there's no other particles to fly away from the beams to replace them. So with time, all the particles that have z momenta are flown away, and you are left with just a box with particles that only have momentum in the transverse direction. So this is our initial condition. So very anisotropic and very overorbit. Yes?
Is this why we can take the coupling to be that small? Since we're not in an energetic enough place for it to blow up?
Well, this is, so the coupling, somehow the hard scale is QS. And so the coupling runs, and the coupling is weak because coupling is evaluated at the scale QS, right? So I'm doing a weak coupling calculation in the very, very weak coupling limit. So I'm basically assuming that QS is large enough compared to lambda QCD, so that alpha S at this scale is weak. And that's the reason for the coupling.
Sorry.
Yeah.
I'm a bit confused about this PZ being very small. I always thought that Hawkland pattern was expanding mostly in the longitudinal direction.
Yes,
and then that seems a little.
Yeah, but in the local rest frame, and we're not yet in the quark-gluon plasma, right? Yeah, this is somehow not yet the quark-gluon plasma, but it somehow it is expanding. So if you look at the kind of, it is so at this point you should better think of it as a free streaming set of particles. It's a free streaming set of particles that are kind of it's a gas that is expanding in one dimension like this. But the particles, the expansion, the particles, if the particles don't collide, they just fly freely. Somehow they have to the system is getting more and more dilute. But the particles are not colliding. So we have a system that is infinite in the transverse direction and then expanding in the longitudinal direction. So translational invariance tells you that, I mean, the PT, the transverse momenta of the particles stay the same. They're not interacting. So we all the time have, nothing is changing the transverse momenta of the particles. But because the system is expanding longitudinally, the particles that have some Z component of the momentum, they fly away. The only particle, if we wait for a little bit of time, the only particle we are left with are the ones that have no Z component.
Wouldn't we then expect PZ from the order of the transverse momenta? Because the transverse momenta has that, they will also fly away.
Yeah, but that requires interactions. That requires interaction. So just the expansion will make PZ small, and it requires interactions to make PZ again of the same order of PT. So it requires interactions to turn this system into a plasma, where particles are interacting enough so that they stay in local thermal equilibrium, and in particular so that they stay locally isotropic.
So you're saying because they started with a lot of PZ,
well, the particles that had a lot of PZ in the beginning were the beams, they're gone. But I mean, and when we're looking at the stuff that is left, the particles that had a lot of PZ, they're gone, and we waited for a little bit of time, and now we're sitting in the center, and the only particles that are left in the middle because they did not have any PZ.
Okay, so I think I have exactly the same problem. So the thing that's doing the heavy lifting for this inequality is the fact that it's an infinite sheet. Yeah, so otherwise high PT things would also have.
Yeah, exactly.
But so they get replaced now because we have this.
Yeah, we have an infinite sheet. So if we sit here, our high PD particles go away, but there are new high PD particles coming from other parts of the transverse plane. Yeah. So this is our initial condition, and so the question is at what QS times tau is, does the occupation number become of order 1 and typical transverse momentum of the order of the typical track, the typical longitudinal momentum and transverse momentum of the same order. So this is the question that we want to answer. So when do we become isotropic, and when does the occupation number go from this overoccupied to something that is of the order of a thermal system? And since we are doing a weak coupling calculation in a one-scale problem, QS, it is obvious that this QS tau, is going to be alpha S to some power, right? And we're not going to care about any of these prefactors here. What we are interested in is what is the power of alpha S here. And the answer from BMS is, I can give you a hint that the answer is -13/5. Right?
Of course.
Of course. You should immediately see it, right? just look at this, and this is the. And this is I will try to go through the different points of the argument that lead to this -13/5, because there's lots of different physics, lots of interesting different physics. One can do, and people have since done kinetic theory simulations where kind of you can track the stages. You can kind of see, okay, the basic procedure works like it is. Maybe exactly verifying the -13/5, it really requires very, very weak coupling. And that's a little bit difficult to do in kinetic theory because everything happens so slowly and somehow it gets numerically a little bit challenging. So I'm not aware of we've been discussing with Aleksi Kurkila that we should just somehow push to the extreme and somehow see really extract this -13/5. But yeah, not so to some qualitatively verified, but not really quantitatively by kinetic theory simulations. Okay, so we start with stage 1, which is classical fields. So we were describing our system with classical fields. And so let's start first with what happens when we keep with classical fields. And first, well, let's understand what happens without interactions. So if we have no interactions, our part of typical distribution, somehow phase-space distribution is of the order of 1/alpha S. So this kind of refers to the distribution of the particles, the hard modes, the particles that there are. Okay, so and also their transverse momenta are constant of order QS, and then PZ goes like 1/tau, because this is kind of just the redshift. So now you may think, how is this consistent? So the way you should think about it is that if you plot this distribution function as a function of PZ, so this is F as a function of PZ, what happens is that you start off with some distribution in PZ. When you go forward in time, this becomes narrower and narrower, but this F is always the distribution at PZ = 0. So the phase-space distribution of PZ becomes narrower and narrower because of the expansion, but the occupation number at PZ = 0 stays constant. Okay. And then we have what I will call NH. So this is the hard gluon number density. NH. So this is the density of these hard scale gluons. And so this is just integral over three-dimensional phase space of this distribution. So number densities, take this phase space density, integrate over free momentum, that is number density. Okay. So this integral is basically, there's two transverse dimensions and one longitudinal dimension. So the integral is basically this times the square of this times this, right? So the number density of gluons now is going like Qs squared over tau times 1 over alpha s. That's how many gluons we have per unit volume in our system. Okay.
Sorry, what's the subscript of the number density?
H for hard.
Oh.
H for hard. Because it's the gluons that are somehow the bottom up refers to the fact that we're going to have a hard gluons and soft gluons. And we start with only hard gluons. And then we're going to end up having everything in the soft gluons. That's when we're finished. So this is the hard gluon number density. So this is without interactions. Okay. So then another thing that you can still have, parametrically, which is in the classical field regime, we can have elastic collisions. Okay, so what changes when we have elastic collisions? So an elastic collision between two, now most of our stuff is in the hard particles. So we can assume that somehow the dominant process when we have elastic collisions is this kind of a collision process. So two p-channel scattering of two hard gluons. Okay. Now this is where the MD by comes in. So this, of course, if you just calculate this in perturbation theory, this cross section will have a 1 over t. The cross section will go like 1 over t squared, and it's infrared divergent. There's an infinite cross section for two gluons to scatter at zero scattering angle. But of course, now we're doing kinetic theory. We're not just doing perturbative QCD. We're doing kinetic theory. These gluons are not interacting in a vacuum. These gluons are interacting in a bath of other gluons. Okay? So this means that this propagator here will have to be dressed with gluon loops. And what this does is that this introduces a scale, the Debye mass scale. It's kind of a thermal mass for this gluon that is exchanged here. So what dominates the cross section is this kind of a scattering where this propagator is regular. It has a thermal mass generated by interactions with the hard particles, which we call the Debye mass. So how do we get the Debye mass? This is kind of the formulation here is known as hard thermal loops, but we will not go into that. We will just say that the thermal mass so this is what dominates is that this being a soft gluon, exchanging a soft gluon, because that's what kind of makes the cross section large. And it stops getting large when this is regulated by the Debye mass. The Debye mass for the soft gluons is generated by hard gluons. So it's generated by having a hard gluon circulating in a loop direction with this propagator. And what happens when you calculate this kind of a propagator is that the Debye mass is proportional to alpha s, and then it's proportional to integral over phase space, this phase space integral divided by absolute value of p. Okay. So basically, because the dominant p here is of the order of qs, this is parametrically of the order of alpha s divided by qs times the hard gluon number density. So the Debye mass is alpha s cancels the alpha s. The Debye mass is qs over tau parametrically. Okay. So here you can actually see that I said that we need to assume that the soft scale is less than the hard scale. So strictly speaking, in the very beginning of our calculation, when we start at qs equal qs tau, because one, this is not yet satisfied. We start in a situation where the Debye mass and the hard scale are the same. But if we just wait a little bit without any interactions, and if the Debye mass is the same as the hard scale, the interactions are really weak because you don't have this scale separation. If we wait a little bit, the Debye mass will become less than the hard scale, and then we have this scale separation, and then we can do kinetic theory. So in the very beginning, we cannot do kinetic theory. We have to do classical fields. Well, now we're going into a regime where both kinetic theory and classical fields have an overlapping region of validity. We can use both, and we get the same physics with kinetic theory and with classical fields. There is an overlap region, and we are now in this. We are now getting to this overlap region. Okay, so good. So the Debye mass dominates elastic collisions, and to erase this at some point. Anyway, so now let's calculate the collision rate for these kind of elastic collisions. So we'll calculate the collision rate. Which is kind of a number of collisions. Now we're looking at elastic collisions per unit time. Okay, so I will just, if you're familiar with kinetic theory from, let's say, statistical mechanics course, you might have seen this, or maybe not. But I will just state that the collision rate is given by the cross section for this process times the. This is relative. This at this point, up to this point, this is relatively quite intuitive. The collision rate is given by the cross section, which is how often do you collide, times the number density, how many particles do you have that could collide, right? And if you look at the dimensions, number of collisions per unit time, this has units of 1/time. Cross section, so units of GeV, energy. Cross section has units of 1/GeV², and the number density has units of GeV cubed. It's 1 per volume. So this has the right dimensions. And this is almost the right answer, except that now we are in an overoccupied system. So these gluons, when they're scattering elastically, they are going into final states where there are already lots of gluons. And these gluons are bosons. So it happens that in kinetic theory, this kind of a process has what is called as Bose enhancement. This is Bose enhancement of that. This is the same thing that makes a laser work, right? I mean, what is a laser? A laser is somehow you have some decays where some metastable state which decays into a state that has a photon. Of course, this can also happen spontaneously. What happens in a laser is that you organize a situation where you're creating a photon into a state where there are already photons, right? And this makes the decays enhanced. You're decaying much more rapidly because you're decaying into a state where there's already a photon, and this is the way you generate lots of photons, and that's how you make a laser. So this is explicitly it's a 1 plus F in the kinetic theory collision rate. If you're going to a state which is already very highly occupied, has many bosons in it, that increases your chances of going there. Okay, and now this F is much larger than 1, because we were starting from this situation where our F is 1/alpha. Okay, so we're completely dominated by this. So we are completely dominated by this F. But at least for now, okay. But of course, you see what happens now is that we have these elastic collisions. These elastic collisions will start to broaden up the situation a little bit. Our number of particles is still going like 1/tau. This will actually, I mean, since we have elastic collisions, so an elastic collision don't change the number of hard particles. So we made this estimate for the number of hard particles for a non-interacting theory, but elastic collisions don't change the number density. So we will still have this many particles per unit volume. But what these elastic collisions do is that they will start generating a PZ. So the particles, instead of just going, they will a little bit limit the PZ going to 0, and they will somehow, you have 2 particles with only transverse moment, and they will scatter off plane a little bit and generate some PZ. So what that means is that our phase space density will start to go down. And so at some point we will go away from this regime. So let us write what the phase space density is. The phase space density is the number density divided by the volume in P space that is occupied by these particles, right? Because if I'm inverting the integral that says number density is phase space in the phase space integrated over momentum. Now I say phase space integral, phase space density is number density divided by the typical momenta. And the typical longitudinal momentum is Pz, and the typical transverse momentum is Qs. So longitudinal transverse momentum, particle number density, F. And since if we a little bit allow Pz to grow a little bit relative to a non-interacting case, this will start going down, and at some point we will reach a situation where this F doesn't dominate over the one. That's the end of the classical field regime. Now we're in a regime where classical fields and kinetic theory both are okay, but at some point this F will go down. We cannot use classical fields. Good. So when does this happen? This phase one. Classical field kinetic theory overlap phase ends when the occupation number becomes of order 1, not anymore 1 over alpha s, because then I have to change my argument for what the collision rate is. Okay. So when does that happen? We will do something that we will do several times in this calculation, and we'll do a self-consistency argument. Okay. We'll do a self-consistency argument which says that this will happen when the Pz squared divided by the lifetime of the system is the same as the rate of change of Pz squared. This sounds really weird, right? But this is a typical argument that you make often in cosmology, especially. So it's kind of saying that we want to we're looking for a steady state solution, right? And in a steady state solution, let's say our Pz will go like time to some power, what power. And this steady, what does it mean that there's a steady state? A steady state means that there's two competing effects which are balancing each other. In this case, it's the expansion is trying to expand. The collisions make Pz smaller. The collisions are trying to make Pz larger. And somehow when we're in balance, the situation we're looking for is what kind of a power alpha balances these two effects. Yes?
Why do we expect F on the order of 1 to be instead?
No. F of the order does not mean that. We're looking for when does F become of the order of 1. And in order to know when F becomes of the order of 1, we need to know how Pz grows, how Pz changes. And what we're trying to now here see is how does Pz change as a function of time. So we kind of everything goes like a power in time. So we know that Pz is going to go like some power of time. And if Pz goes like some power of time, then in this situation, we're looking for a steady state situation where Pz goes like a power of time. And in this situation, the time derivative is proportional. Is somehow it's a power law. If it's a power law, a steady state power law, its time derivative is the same up to a constant, the same as the thing divided by time. Yes.
Sorry. Why in a steady state do you expect Pz to go like a power of time?
Well, everything goes like a power of time. So everything goes like a power of time, and this is what we will see. This is one way to we will see powers of time, but I think this argument is a little more general than kind of okay. Pz over how do I change? how should I, so these kind of processes, the PZ broadening from this process becomes, the question is this important? And this is important when kind of a typical gluon during the lifetime that it experiences has at least one collision that is making its PZ, changing its PZ. So it's kind of a self-consistency argument that kind of, okay, when the rate for something happening is the same as the lifetime of the system, then that something happening really dominates that the thing that is happening has happened at least once in the lifetime of the system. And that's what's required for this thing that is happening to somehow affect it. You know, if something happens too rarely compared to the lifetime of the system, we can neglect it. If it happens too fast compared to the lifetime of the system, then it's going to drive our system to some other behavior. So we're looking for the steady state where kind of the lifetime, when the lifetime of the system is of the same order as the rate for this thing to happen. So we're looking for a solution for when does PZ over the lifetime of the system equal the time derivative of the change of the typical PZ squared. So when does this happen? Let's calculate. How does, what is this? Okay, so this is in such a collision, I said that this is kind of the momentum exchange here is dominated by device K. So what's going to happen in this collision is that the PZ is, remember, these only have transverse momentum, and this collision is an off transverse plane collision that is giving them a little bit Z momentum to the finals. It's broadening the Z PZ. So typically, because this is dominated by gluons of the order of MD being exchanged here, it means that in such a collision, the amount of PZ that you will get is of the order of MD squared. And then how often does this happen? Then it's just a collision rate. Number of collisions per unit time. Number of collisions per unit time times the typical PZ that you get in one collision. That is the rate of change of the typical PZ squared. And we're looking for when is the rate of change of the typical PZ squared of the same order as PZ squared divided by the lifetime of the system. So very sketchy. It sounds very sketchy, this kind of argument. It sounds very sketchy, especially in cosmology, you do it all the time.
Why do we care about PZ squared here, not just
It's just somehow easier. I don't know, we could do the same thing for PZ. PZ squared, but
it's funny dimensions.
It would have funny dimensions. This is somehow more natural. I think you should come to the same conclusion, but since here is kind of the propagator is just dimensionally, it's more natural to calculate the typical momentum squared from this construction. It essentially, it would, I mean, you could cancel, it would, I think it would cancel in the end. When you do the self-consistency argument, it would do the same. Okay. So let us, how do we want to go? Yes, let us see what is our, oh, and then one more thing. I, of course, need the cross-section for this elastic, collisions. I forgot that. So the cross-section for this kind of a process. First of all, cross-section has dimensions of 1 over energy squared. It's dominated by this MD squared. So dimensionally, just dimensionally, the cross-section is going to go like MD squared. The part of it is as Matt told you, that these are small angle collisions. These are hard particles exchanging a soft momentum. So they are very forward. And Matt told you the cross-section for in QCD, when this is a spin 1 particle, the cross-section doesn't depend on the collision energy. In high collision energy, this forward collision, cross-section doesn't depend on collision energy. It only depends on the transverse thing here. So cross-section goes like MD squared, and then there's 2 powers of coupling to square the amplitude altogether. This cross-section goes like alpha is squared. Okay. So now our rate of change, collision rate, the collision is the cross-section. alpha S squared over mdy squared times the number density of hard particles, which is qs squared over tau 1 over alpha s, and then the Bose enhancement factor here, which is let's extend this a little bit. So the Bose enhancement factor is this same thing. So qs, so the number qs over tau 1 over alpha s. So the Bose enhancement factor is the same number density. So I'm writing it another time, divided by 1 over pz and space and qs squared. Here. Okay. So I just put in our estimates for how much pz is gained, what is the cross section, how many particles are there participating in these collisions, and a Bose enhancement factor saying that, oh, I have a very densely occupied system, so these are Bose enhanced. And now what you see is that this is the typical for this self-consistency argument. You see there's a PZ here and a PZ here. So now this is an equation that we can solve. And this is an equation that we can solve, and this equation will tell us how much actually, how the typical PZ of these particles is actually evolving as a function of time because of these elastic collisions. It's not going to go like this anymore. Non-interacting theory goes like this, but because we have interactions, it will have a different dependence. So there's a few, let's see, maybe I can even do this without cheating. All the alpha S's of this one go away. Okay. This, by the way, is a signal that I'm still in the classical field regime. This is a behavior that I can see doing 3+1 dimensional classical field simulations. And in the purely classical theory, I can scale out alpha S completely. Purely classical theory with occupation number 1 over alpha S. If the occupation number is 1 over alpha S interaction goal, I can scale out alpha S completely. So the fact that alpha S scales out from this equation tells me that this is still physics that I can describe in classical field theory. I just have to allow for Z components of the moment. So alpha S goes away, md squared goes away, some of the qs squares go away, and then I take this pz up here, so I get pz to the power 1/3, and then qs 1 over tau, 1 over tau, 1 over tau. I multiply this tau over here, so I get 1 over tau on the right hand side. So this means that I can write this. The natural way to write it, the pz is qs. This gives the dimensions, and then qs tau to the -1/3. Yeah. So this is how. So my PZ is still going down, even because of the interaction. In some sense, the expansion is still winning, but the expansion, because of these elastic collisions, the expansion is not winning by as much. Okay, so I'm a little bit gradually getting closer to isotropy. Right. So still now I know how my PZ is going down, and then I can plug this into here. And now calculate how does my F go? My F goes like qs squared over tau alpha S. That was what we had for the NH. Then 1 over qs and qs tau to the -1/3. That comes from the typical PZ. And then 1 over qs squared. Okay. So, and something is a little bit. No, this is okay. Okay. So I can simplify the qs squareds. And so F goes like 1 over alpha S. And I have QS tau, and then QS tau times minus 1/3. So I am left with all over QS tau to the minus 2/3. This is my okay. So I told you that we have been working with the assumption that f is much larger than 1. So now we can answer the question of when does the third stage of the EMSS end? F equals 1 happens when 1 over alpha s times QS tau to the minus 2/3 is of order 1. So stage 1 ends when QS tau is of order alpha to the minus 3/2. Now you're starting to see the way how these funny fractional exponents of alpha come in. Okay, so our first stage, kind of the classical field kinetic theory stage, dominated by elastic collisions, is going to end when QS alpha is of the order of alpha. The QS tau is of the order of alpha s to the minus 3/2. Okay. We have reached the end of the first stage. It's a four-stage process. We are now at the end of the first stage. And gradually we are going to get weirder and weirder fractions for the exponents. Any questions so far? Everybody's fully satisfied with this.
This is gloriously Almula.
This is very Almula. Yes.
Anyone's wiggles.
Yeah.
So is this behind the scenes a very well motivated argument for every step?
Yes.
Can't be any other way.
These are some of the people who made this argument are some of the smartest people in the business.
Yes,
and they knew what they're doing, and this really shows that somehow. And then somehow other people came on afterwards and did a lot of work in kinetic theory numerics and somehow qualitatively see the same thing. And so, but it requires a lot of experience to really. I would not have been able to come up with this argument somehow given the initial problem. Okay, I would have. Yeah. It's very the difficulty is identifying what is the important physics. Afterwards, it seemed very clear, but somehow beforehand, I mean, it really takes a lot of skill to make this argument. And this is, as Herbert said, this is typical Almiller. He has he has the skill of identity, knowing which kind of physics exists and being able to identify what is the relevant physics for which situation. Good. Now let's go to stage 2. We can still do stage 2 before we take a break. Natural to take a break between stages 2 and 2 because we have four of them. Stage 2. Until now we had only hard particles. They were interacting and exchanging some soft particles. The soft particles were just exchanged in the collisions. But in stage 2, soft particles start to play a role. Soft particles are starting to play a role. Okay. So in addition to these hard particles, which are undergoing elastic scattering, we started with only the hard particles. So you can create soft particles. How do you create soft particles? You need to radiate from the hard particles. We started from the assumption of that I have written this in this way. we need to radiate soft particles. We had this kind of so far we had this elastic process, but in addition to this elastic process, you can also there's a corresponding inelastic process. So what is the process? What is the process at which you produce soft particles? So soft particles typically happen in such a way. And in order to have, I mean, you have to add one more coupling constant to make this process happen. In order to not make the cross section too small, what needs to happen is that as many of the internal propagators as possible have to be soft. So the dominant for this kind of a process, so hard, hard, soft, hard, hard, is that both of these propagators go like R1 over md squared. And these are the kind of the tricky thing about kinetic theory is that you need to have a kinetic theory that includes these kind of processes in order to be able to simulate numerically this physics. So you need to have a kinetic theory, and actually the way you do it in kinetic theory is that you have a kinetic theory that integrates this out and has a 1-to-2 scattering process. This is the QCD effective kinetic theory. So actually the kinetic theory calculation has a 2-to-2 and 1-to-2 process. And the 1-to-2 is kind of an effective treatment of this 2-to-3 process, which is accurate at leading log. Okay, so soft particles start to appear through this kind of processes. What is the momentum of these soft particles? So soft momentum scale soft momentum scale is that a soft square. So each of these collisions, typically the momentum that you generate for these soft particles is mv squared. And then kind of the confused by almost why is this why does the argument go like this? But the argument somehow goes that the argument is that this soft scale is a bit weird because it's not the typical momentum of the soft particles, I think, would be md, but somehow the argument here goes that the soft scale is given by the md times the number of collisions that produce these soft particles. And this number of collisions, d squared, is again going to be the cross section. Now the cross section for this kind of a process is alpha squared to get this squared qs cubed over alpha s qs tau. Yeah, so this is yet now before times tau. Yeah. So this would be the typical MD momentum given. Actually, yeah. So this. Oh, I'm going ahead of myself. Not be drawing this yet. Soft particles appear. So the first time soft particles appear is in this kind of conditions where two hard particles collide. Sorry for mine. Two hard particles collide, and sometimes they generate a soft particle. This is why I have this kind of a alpha squared or ND cross section, and this is the number density of hard particles, and the number of collisions is the collision rate times the time, and now we have forgotten the Bose enhancement factor already because we're kind of going into a regime where it doesn't matter that much. So
it's exceptional if you have two energetic things.
Yeah, and so this
colliding.
Yeah,
that one of them is soft afterwards, and wasn't one soft before.
This is a bit.
Yeah,
this is a bit weird, but I'm not sure. I'm not sure how much we need this in the end. But because mostly when we really generate soft particles, we will somehow start doing getting them from the radiative process. But anyway, so this kind of a collision is the Gauss cancel. This kind of a process, the Gauss cancel and these cancel, everything else cancels except that we have an alpha s times qs squared. So there is such a kind of a momentum scale in the problem, okay, which comes from this kind of a 2-to-2 collision rules. But as you said, this is kind of very weird and rare. Okay. Very easy. So now let's consider radiation. Maybe the reason for this was that kind of we should neglect this at this point because then we can. Yeah, then now we go to radiation. So now we are producing hard. So kind of the dominant way of producing soft particles is this kind of a radiation. This is this propagator is 1 over nd squared, and this propagator is nd squared. So now the cross section for this process, again, dimensionally cross section is always 1 over squared. Now the cross section is alpha s cubed. This is the cross section for this is the cross section for the 2 to 3 scattering. This is the Bethe-Heitler process. This isn't referred to as the Bethe-Heitler process. So BH. So yeah, so this elastic collision producing soft would be like this, but the cross section for this radiative process, which is the important one, goes like this. Okay. So now let us try to understand the soft gluon number density. So the number density for you start having soft gluons, how many of them are there? Okay. So what we do to get the soft gluon number density is that we say that it can be the lifetime of the system, how long we have time to produce these, times the collision rate. This Bethe-Heitler rate for producing these soft gluons. So then again, I have tau. So the rate is alpha s cubed over mv squared. The rate is the cross section times the hard number density squared. I need 2 of these. Previously, I had 1 NH because I was kind of calculating the momentum change of 1 hard particle. So the momentum change is proportional to the number of particles that you can scatter off. But now I'm calculating the change of rate of generating new particles. So it's kind of proportional to the number density of this guy times the number density of this guy. Okay. So number density squared. And then in principle, I could have the 1 plus x, but now I'm neglecting these because somehow not important and not particularly large anymore, not parametrically enhanced. So I'm forgetting about the Bose enhancement. I'm forgetting about the Bose enhancement now because I don't have these start to become important when I don't have that many hard particles. So this is the number. This is my number density of soft particles. Right. Yes. So I put these, and then I remember that at this point, my hard particle number density is still Qs. So this is still Qs squared over tau alpha s, the number density. Yeah, this is still the case, and will be the case for some time still. So I put these together. Let's see what I get. The number that I get a tau. Then I get alpha s cubed over md squared. Then I get qs to the 4. And because it's this squared, alpha s squared and tau squared. Sorry for the small letters. And then I don't have a Bose enhancement anymore. Yes. So this is my result. So altogether, this is alpha s qs to the, what do I have? Alpha s qs to the 4th over alpha s qs to the 4th over md squared tau. This is a yes. Thanks. It's a very now I understand what I need this soft momentum scale. Yeah. Okay, so now I am starting to have yes. Sorry, it's been a while since I went through all of this. Now I understand what I need. So considering this kind of a process, we consider two things. Yeah. Sorry for the confusion. We consider this process as soft hard to soft hard scattering, and this soft hard to soft hard scattering tells us what is. Whereas then this Bethe-Heitler process tells us how many of these soft particles we have. So we use this radiative process that generates the soft particles to tell us what the number density of soft particles is. This number density of soft particles is alpha s qs to the 4th over md squared tau. But once these soft particles have been generated by this process, they start colliding with the hard particles, and they get some momentum from the hard particles. And the momentum they get from the hard particles in each collision is md squared. And the total momentum that they accumulate is the momentum per collision times the number of collisions they undergo. Sorry, I was confused myself. So now we have soft particles. We have this many soft particles. And the typical soft momentum, the typical momentum of these soft particles is this. Good. So now, so the next thing, why do we need, what do these soft particles now do? They have somehow, their momentum is not going down. So they're kind of somehow having some real oomph to them. So what happens next is that the soft particles start to influence the Debye scale. Until now, we calculated the Debye scale, assuming that only hard particles go in this loop. And we came to this result for the hard particles. Yeah, the hard particles give this kind of a Debye scale. So now let's see what these soft particles do to the Debye scale. So soft contribution to Debye scale. So in the same way as we calculated hard particle contribution to the Debye scale here was alpha s times the density of hard particles divided by the typical momentum of the hard particles. So in the same way, the soft particle, the soft particle contribution to the Debye scale and the squared kind of soft contribution will be alpha s times the number density of soft particles divided by the energy scale of the soft particles. Okay, so I'm kind of considering separately the soft particles going around this. Note that these soft particles are not necessarily at the device scale. They're kind of potentially harder than the device scale. And the momentum is potentially harder than the device mass. So let's plug in these numbers. So the soft particle, so this is alpha S. Soft particle number density is alpha S qs to the 4th over md squared tau. It's funny that I have this md here. And then I have the square root of this. So square root alpha S qs, right? Square. This is the ks, which is the square root of this. Okay. So so from these we can invert and from these, so what we now have is two. Okay, so this is kind of the soft particles scattering with soft particles. We have a self-consistent equation. Just forget this off here. We have a self-consistent equation again from which we can solve the soft particle Debye mass, and then we can plug this. So let's see what this gives. This gives us that the soft particle Debye mass is I multiply md squared, so I basically need to take the square root of this. So I have here I have alpha s to the 2 minus 1/2, so 3 over 4, and then I still need to take 3 over 2. Yes, this is alpha s to the 3 over 2, and then because I have md to the, I multiply this, I have md to the 4th, so I need to take the square root of this equation. So what I get is that the soft particle Debye mass is alpha s to the 3 over 4, and then the rest is dimensions. So I have qs to the 4th, and the square root qs squared. I have a 1 over tau, and I always keep the tau together with qs, so it's qs, so it's this qs tau, and then to the 1/2. 1/2. So this is the Debye, kind of the Debye mass calculated from the soft particles. And we see that the hard particle contribution, the Debye mass was going down like 1 over tau. This is now only going down like 1 over square root to the tau. So at some point this takes over, and it's the soft particles that determine the Debye mass, not the hard particles. Depends, of course, on the coupling here. Here you have this is suppressed by a coupling. But it wins at later times, and it's going to win at some time. How? And we can later determine what that time is. We can also plug this in here and calculate the soft particle number density. So I take this md squared, plug it in here where I have an md, and I will just write the result because I will not be able to simplify them otherwise. Alpha s to the 1 over 4. And qs cubed over qs tau to the 1/2. Basically, this is I have md squared times tau, so this md squared times tau, it's a tau to the plus 1/2. Which goes down here. So it's again square root of tau in the denominator. Good. So this is now our soft particle, the Debye mass of the soft contribution of the soft particles to the Debye mass, and the number density of the soft particles. And at some point this dominates. And how do we calculate when does it dominate? So let us calculate when stage 2 ends. I guess one can do this in. So of course one needs to be a little bit somehow, one can do this argument a little bit. One can go, there are several places in this argument where one could in principle go back and check and see that the assumptions were self-consistent, and I will to skip over.
Stage 1 and stage 2, one could now see whether these things somehow interact by the
Yes, yes. So in several places I could go now back and check that, okay, well, how are my soft particles in stage 1? I didn't do that. I'm just kind of, these guys have thought about it, and we have a limited amount of time, so we're not going to make all the checks. That I'm kind of going to tell you how it works, but if you want to make sure, there are lots of things that you can check, you can check afterwards. So when does the stage 2 end? The way they want to somehow calculate, and I'm wondering if one could. One could maybe just compare the Debye masses, but no, the argument is not that you're not comparing the Debye masses. You're looking at the stage 2 ending when the number density of soft particles becomes similar to the number density of the hard particles. So the soft particles start growing, and soft particles start growing, but they are still during the stage 2. The hard particles kind of dominate the thing, but the soft particles, the number density, the soft particles start to overtake the number density of the hard particles when this happens. So we can see when this happens. So this is when alpha s 1/4 qs cubed over qs tau to the 1/2 from here is similar to the number density of hard particles, which has all the time been qs over tau 1/s. That is qs squared over qs tau times 1/alpha. It was cubed. It was cubed. So I cancel the qs cubed here. I look at the powers of qs tau, so I multiply this over here. So I get qs tau to the 1/2 is alpha s to the -1, alpha s to the -5/4. So this is a qs tau of the order of alpha s to the -5/2.
5 was, of course, very important.
5 is very important. 5 is very important. Let me check. Yes.
What was it? 30?
13/5. 13/5. So yes, we are getting there. So now we have checked stages 1 and 2. Our first stage ended when qs tau was, and remember alpha s is very much less than 1. So all of negative powers of alpha s are positive numbers. And the bigger the negative power, the bigger the problem. So between alpha s equals -3/2 and alpha s equals equals -5/2, our system has been in a stage where it's mostly dominated. Both the number density and the energy are dominated by the hard particles, but there's a growing bath of soft particles that somehow, and this at this point, the soft particles are taking over. And there are lots of, I think, self-consistency thing.
Maybe for the data, can you compute the data mass?
Yeah.
You first said the contribution of the soft, but then the right-hand side, you said, well, let's just take the soft, and so you kind of assume that.
I kind of assume that it's, yeah. So I kind of assume, so here in this Debye mass, I just assume that this is the contribution of the soft particles to the Debye mass.
First, when the soft one contribution is this
yes.
over this, and then you go, and this is just the Debye, but let's just do the soft.
Yes, yes. Yes, so exactly. So I used the. So I think there's a lot of, but I think basically, well, we could check. We could check. Let's see. What is the if QS tau is if QS tau is alpha to the -5/2, then the mdy squared soft is over QS squared. So this is at QS tau is 1/2. So this is -5/4 downstairs. So it's 5/4 upstairs. So this is alpha S 3/4, alpha S 5/4. So alpha S squared. And the hard particle contribution to the Debye mass is, we have calculated it somewhere.
Just the QS over tau on the bottom of the output.
It is still QS over tau. So it's kind of funny that the soft particle contribution, the soft particle contribution to the Debye mass is still kind of parametrically small in alpha, but then for some reason that's the thing that you're, maybe it's the Debye mass of the soft particle. Funny that somehow there's weird things in this argument. There's weird things in this argument, but let's take a break here. Let's take a 5-minute break. And good. So with the help of our students here, we refined the arguments during the break. So kind of the stage 2, we calculated the ending condition from saying that the soft particle and hard particle energy number densities are the same. And there was the question of why were we justified in using the soft particle contribution to the Debye mass in our calculation of the soft particle. So now if you go back and check, now at this stage, at the end of the stage 2, which we have determined from the number density here, we should, for consistency, we should go back and check what are is it really the soft particle contribution to the Debye mass that dominates here? And in fact, it is, because if we go back to our hard particle contribution to the Debye mass goes like QS over tau. So we can write this as QS squared times 1/QS tau. And now at the end of stage 2, QS tau is alpha S to the -5/2. So at the end of stage 2, the hard particle contribution to the Debye mass goes like alpha S to the 5/2. But the soft particle contribution to the Debye mass goes like alpha S squared. So indeed, at the end of stage 2, the soft particles do dominate the Debye mass. And alpha 2 is much less than 5/2, right? So indeed, at the end of stage 2, the soft particles dominate the Debye mass, and our calculation here was justified in using the soft particle contribution to the Debye mass, calculate the number density of the soft particles. Okay. Good. So now we're safe. Then we actually, I realized there's not 4 stages. There's only, I combined stages 1 and 2 into stage 1. So now we're already at the last stage. Okay. So now we have come to the switching point at the end of stage 2 when the soft particles and hard particles have the same number density. And of course, when we go forward from this into the next stage, the soft particles will be more numerous than the hard particles. So now we are at the stage where the soft particles dominate the number density, but the hard particles still carry the energy. So when QS is much larger, so the hard particles still are. The energy of the system is in the few hard particles, and the number density of the system is in the many soft particles. So in order to reach thermal equilibrium, the hard particles need to lose their energy. And now they're going to lose their energy by radiative energy loss. There are a couple of hard particles, and they're flying through this plasma of soft particles, and they are going to lose energy by radiation. Okay? And
So you're thinking induced radiation.
Induced radiation. So the hard particles are going to lose their energy in a process like this. They are going to interact with this. So this is hard, and these are soft particles. This is a hard particle, and this is a, and this is a, let me call this, this is a branching. Okay, so the hard particles are going to lose their energy by scattering of the back of many soft particles. And in order to do this correctly, one has to go into another field of physics, which of course Al Miller also knows, which is jet energy loss. So we have to calculate this energy loss in a way that is consistent with LPM, Landau-Pomeranchuk-Migdal effect, meaning that we have to take into account the fact that this radiation process takes time, and during the process of emitting this gluon, so the hard particle is going to lose energy by emitting a gluon. This gluon is going to carry away for energy loss. And we have to take into account that during the time that it takes to emit this gluon, you're going to have time to scatter off several parts of particles in the medium. And these need to be somehow treated coherently. Okay. Good. So we are going to emit a gluon with some transverse momentum, and I think the gluon is going to carry away some. Some K branching longitudinal moment. Okay. And then it takes a certain amount of time for this gluon to form, and this gluon is being radiated at some angle theta. Right. So the angle theta is K curve over K branching. Right. So this is the opening angle in this radiation, and this whole emission process takes time Tf, so formation time of this radiation, and somehow basically the idea is that while you're still busy emitting the previous gluon, you cannot start emitting the next one. So that's how you do the calculation. So that you have to properly finish emitting the first gluon before you can start emitting the next one. And how long does it take for you to properly emit this gluon? The gluon kind of needs to be far away from you, from the emitting jet, so that it's kind of not anymore.
So you can distinguish it.
So that you can distinguish it. If the emitted gluon is at the same coordinate, it's still a part of the emitting part. The color interactions with the medium don't distinguish. Okay. So, how long does it take? So, well, during the time Tf, this coordinate R, during the time Tf, this emitted gluon it goes with an opening angle. So the R, how far does it get in transverse coordinate from the emitting particle is determined by the formation time times the opening angle, right? And so this is a T formation time times K curve over K branching. K branching is the longitudinal momentum. Okay. And in order for this really to have fully happened, this needs to be of the, this is yeah, I have a typo in my notes. It doesn't make sense otherwise. This emission has happened kind of when the gluon is separated from the emitting parent by more than 1 over the transverse wavelength. More than one wavelength, and wavelength is 1 over the transverse moment. So this separation has to be of the order of 1 over K curve, and this is when this gluon emission process is fully finished. So from this we can solve that the formation time that it takes to the formation time that it takes to emit this is K branching divided by K per squared. Okay. So the larger the momentum you lose, once you know, more energy you lose, the longer time it takes to lose it. But the more, if you do this emission by having a larger transverse momentum, then the emission happens faster. So this is the formation time of one radiation. Okay, and and somehow the effect of this LPM interference is precisely this, that now you can only, I mean, while you are still, you can only be emitting one gluon at a time. There's a destructive interference if you're trying to start the emission of another gluon before the other one is, first one is yet finished. So kind of this leads to the this kind of argument that it takes this long to do. Okay, so now how much do we now have of these scattering centers, these soft particles in the medium that we are scattering? We need to calculate the mean free path. So lambda is the mean free path, and I will calculate 1 over mean free path. And the mean free path is the number of soft particles, which are my scattering, density of soft particles, which are my scattering centers, times the cross section. And this is now the cross section for one of these scatterings, right? So this is actually really, what I'm really doing is that I have a soft particle here, and each of these is actually scattering off some soft particle in the medium. So I'm losing energy by scattering of the soft particles. And the mean free path, how long does this hadron have to travel before it encounters one, or this gluon have to travel before it hits one of these vertices, is the mean free path. One of the mean free path is the number of scattering centers times the cross section. These are, of course, mediated by md squared. Md squared is the typical momentum of this gluon exchange. So I think probably, yes, my cross section is going to be alpha s squared divided by d by mass squared. It's again the 2-to-2 cross section here, but now it's part of a coherent energy loss scenario. So this is not a scattering by itself; it's part of this process of emitting this. This gluon. Good. So and the KT. What do I then do? Now, how much transverse momentum did you get in this? How much transverse momentum do you get in this this kind of a scattering? Well, you have to count how many. In some sense, the way you count the transverse momentum that this emitted gluon accumulates, the kind of the transverse momentum has to come from this medium. So the way you count the transverse momentum is that in one of these interactions, you get off the order of md by transverse momentum from the target. And then you have to count how many of these medium interactions you have time to have during the time that it takes for this branching to take place. So how many of these kind of medium interactions you have? Well, it's the formation time divided by the mean free path. This is what tells you how many medium particles you interact with. And this is telling you how much transverse momentum you get from each of these medium particles, each of these lines. Okay. So putting now these in, let's see, we get which one, what do I want to solve? I want to solve 1 over formation time from this. So this is 1 over formation time is md squared over k perp squared, and 1 over formation time is 1 over lambda here. And then this is on the other hand, 1 over this is k perp squared over branching. Is this the way? I know this is not the way I want to do it. I want, let me do this one. So this is md squared tf f times then ns alpha s squared over md squared, right? So now I have that. And on the other hand, I want to eliminate this k perp. So this k perp solving from here is also k branching divided by EF, right? Okay, so here I have an equation where I have eliminated this typical k perp, and I have calculated, I can solve this cancels, and I can solve that 1 over TF is, I need to take the square root of this equation, so it's alpha s, and I'm taking square root ns divided by square root k branching. And I should have alpha s squared. No, alpha s, yes. Okay. Good. So this is the formation time for how long it takes to emit one of these gluons. And then the emission rate, which is different from the formation. So the formation time tells you that if such a collision, such a gluon emission happens, how long does it take? The emission rate tells you that, emission rate tells you that how often do these happen, and so the emission rate is given by the probability to do this emission times the time scale times the divided probability to emit times the rate of how fast this emission happens. So the branching rate, so the emission rate, which is 1 over tau branching, is a very weird. Why don't I have any alpha other MDs here? That's the way it goes. So so the emission rate is, if I take the inverse of this equation, the typical time between emissions is the formation time, how long does the emission happen, divided by alpha s, because there's an alpha s required to do this emission in the first place. So this is kind of the square of this alpha s here for the actual jet emission. Okay, so this is now alpha s squared, square root of soft particles over k branch. Okay, so good. So now we come to our approaching the end of our thermalization process. So when the stage, but still a couple of things to do. So now we have hard particles are carrying the energy, and the soft particles are by radiation. And now we again have to solve a self-consistency equation. And the self-consistency equation is kind of about energy balance. So the soft particles have some kind of an energy which is growing because the hard particles are losing energy. And the energy of the soft particles determines the number density of the soft particles. And the number density of the soft particles determines how quickly do the hard particles lose their energy. So I have kind of a system, coupled system where the energy of the soft particles and the energy of the hard particles influence each other in two ways. So I need two conditions. One of them saying that the energy of the soft particles grows because the hard particles lose energy, so the energy balance equation, and the other equation is should be telling me that the density of the soft particles, and the density of the soft particles affects the emission rate at which this energy loss happens. Okay. So let's look at the first one. So first, in order to get this, we need to somehow, and we want this process to convert. We want the hard particles to lose all of their energy. Okay, and somehow the end state of this process is when the hard particles have lost all of their energy. And here again, we come to make the same rate of change equals 1 over inverse age of system argument that we did for the PZ in the beginning. So we say that this branching rate is going to have to be the same as the age of the system. And this is when you have lost, and this is the time scale at which the hard particles lose all of their energy. When the branching rate for this energy loss incurring radiation is the same as the age of the system. So here, okay, so let's and then let's plug in this 1 over tau branching. So the 1 over tau branching is alpha S, and then the density. Now I will introduce, so T is the temperature of the soft particles. So here I had the density, number density of the soft particle under the square root. So the number density of particles, massless particles, is the temperature to the third. And then I have this K branching square root here. So from this, I now solve that the K branching, the typical amount of energy that is lost by the hard particle in this collision is.
So here, right, you switch to a thermodynamic notion of what the soft particles do, and you treat them as gas.
Yeah. And I have a alpha squared here. I had an alpha squared here. I was just doing a little bit. So the branching, the energy that is lost in one of these emissions, the K branching, it's alpha S squared, tau squared times T cubed, which is the number density. And so that, and then I look at the other equation is the energy flow. So the other equilibrium equation is what I said, that as the hard particles just are losing energy, and in every kind of gluon emission, they're losing this much energy. And that energy lost by the hard particles has to go to increase the temperature of the soft particles, and therefore increase the density of the soft particles. So the other equilibrium equation that I write is that I say that the K branching, which is the energy lost in one collision, times the rate, the branching rate. How often do the energy lost in one branching times how often do the branchings happen? Has to be, which is a branching times the number density of the hard particles divided by the branching time. So branching time is about how often one individual hard particle is scattering, and then the number density is how many hard particle radiations do I have overall, integrating over all the hard particles in the system. So this is the energy that is lost by the hard particles per unit time. And that has to be same as the change in the energy density of the soft particles. So the soft particle energy density is the soft particle temperature to the fourth divided by per unit time. So the rate of change of the soft particle energy density, which is now temperature, rate of change of the soft particle temperature times T cubed, right? So here I have a couple of equations which from which I can from which I can, and I still need from which I can solve everything. Let's try to do that just to be sure. So we need to plug in that K branching. So from here, let me say that K branching is I solve K branching from this equation. So this is T branching over NH T cubed rate of change of temperature d tau, and then here I insert the a smarter way to do this. Although there's a better way to. There should be a smarter way to do this. Overbranching. Let's just do it. So the how okay. So how branching is T cubed over square root A. Branching 1 over alpha s squared. The number density of hard particles is 1 over the number density of hard particles is alpha s over. So qs over tau alpha s was the number density of hard particles. No? So this is actually I already know that it's 1 over tau. Yes, that's right. So this is actually better. I already know that T branching is the same as tau, right? And then this is n number of hard particles is q squared tau alpha s in the inverse, d cubed dt over d tau. And this, on the other hand, is goes like alpha s squared tau squared t cubed. So T cubed cancels.
To the fourth, you had that.
To the fourth, yes. T cubed cancels. So let me, then this equation solve T temperature over d tau. Is this what I want to do? Yeah. T temperature over d tau. So this is the temperature of the soft bath. It's going to be alpha s cubed, I guess. And then I have these taus cancel with tau squared. And then dimensionally it is us squared. So from this I deduce that the temperature, because of this energy loss, the temperature of the soft thermal bath grows linearly in tau. So everything else is kind of getting cooler and diluting all the time, and now the soft bath is somehow instantaneously it is regaining all of the gaining energy at a huge rate. Okay, and now what we still need is the other condition. Now we know that how the temperature is growing. And we calculate, come back to this K branching. So the K branching is alpha S to the 4 tau squared temperature cubed. So this is alpha S, alpha S to the 9 Q alpha S to the 9 QS to the 6 and tau cubed. Okay, this is our K branching, and now the closure equation. When is it that we have lost all the energy of the hard particles? That's when we are thermalized. So the hard particles have lost all their energy when this K branching is the same as the energy that the hard particles had to begin with. Okay. And so here you see this is tau to the 5th, alpha S to the 13. So we realize that the hard particles have lost all of their energy when US tau is over alpha S to the minus 13 over 5. And in my notes, I also have what the final temperature is and the final number density in terms of alpha S and QS, but now we can plug them in here. But I think this is a good place to stop. So I will just somehow, so this is an amazing calculation. I didn't do it as you see, I was struggling with a couple of points in between because it really requires you to understand a lot of different kinds of physics. So just to recapitulate, we started off with classical fields, boost invariant classical fields, things going down as because of the boost invariance, things are going down like 1 over tau. Then we said that, okay, there are a little bit of elastic collisions. I didn't explain you why the classical theory only has elastic collisions. But well, I can say that classical theory only has elastic collisions because classical theory, everything is Gaussian enhanced and somehow the elastic collisions are, I think it's the Gaussian enhancement is what makes inelastic collisions irrelevant. So then we have a little bit of elastic collisions that somehow a little bit are kind of switching, affecting the moment of our particles. This eventually leads to the number density of the phase space density of the particles going down. At some point you go out of the classical regime and you have to worry about, then you start to have to worry about quantum scattering, so it's kind of things in the dilute regime. And then you have the gluon emission, the emission effect of the emitted gluons. They scatter all the hard particles, get some energy. They affect the Debye mass, which again affects the rate at which all the collisions are happening. Finally, you end up with lots of soft particles and a couple of hard particles. Hard particles are traveling through the soft particle path and losing energy. And finally, at this time, the hard particles have lost all of their energy. And so this is the QCD recoupling result. Maybe I will draw one figure that illustrates. So what of physics? This is often illustrated by something that I call the, it wasn't in this form, the plot, yeah.
So the soft particles kind of come from the hard part. Right?
Yeah.
And so why would they start at a lower temperature?
Because they are soft. That's what it means to be soft. The temperature means, so the particles during this process, once they are generated, they are soft and they interact strongly and they are all the time in equilibrium. And that's what the temperature means, that the temperature is the typical momentum of the soft particles. And it starts very small because there are in the beginning not that many soft particles. But then when these hard particles start losing energy to the soft particle band, starting from QS tau equals alpha to the minus 5 over 2, then the process it's really an explosion. I mean, everything somehow, the stage going to alpha, the stage going from QS tau equals 1 to alpha to the minus 3 over 2. That's an eternity. then things start getting faster. Alpha to the -3/2 to -5/2. That's already a little bit faster. And then after alpha to the 5/2, between alpha to the 5/2 and alpha to the 13/5, this is not that much more than alpha to the 5/2, right? But a huge explosion happens and somehow the system dramatically changes. So let me just draw this. This is somehow often illustrated in a what I like to call the Kurkela-Joux plot. Okay, so this is the let me get this. So this is the anisotropic EP over PL, where this is 1, so this is thermal equilibrium, and this is the typical occupancy. So the typical occupation number, and let me draw this as alpha S. Alpha S times the typical occupation number. So our starting point is somewhere here, or this is 1. We start off from a overoccupied system, so alpha S times the occupation number is of order 1. And then thermal equilibrium is down. Thermal equilibrium is down here. So thermal equilibrium is occupation number is 1, so alpha times the occupation number is alpha. And the anisotropy is 1. So transverse pressure over longitudinal pressure is 1. So the way the process goes is that first there's the stage 1, the classical field state. The system is getting more and more anisotropic. Then at some point the anisotropy stops growing a little bit more, but then at some point you start going into an underoccupied phase. Right? This is when F becomes much less than 1. The hard particles, the hard particles start becoming anisotropic. The occupation number goes down, but then they start, because they're underoccupied, the quantum scattering, somehow quantum scattering. And then you come back and your anisotropy starts to go down and your occupation number starts to go up again, and then until you hit the thermal. So the system makes this kind of appear. So this is like stage 1. Somewhere here is stage 2, and this is stage 3. It makes a huge detour. It has to, even if you start from overoccupied, it has to become underoccupied before it can really become thermal. And even if you would start from relatively close to isotropy, because of the expansion, you first have to become very anisotropic before you can start, before the processes that really break this anisotropy can become efficient again, and then you get back to isotropy. Good. So this was the alpha to the -13/5 that I promised. I think this is a good point to stop.
Thank you, Tuomas.
Like you see, I was struggling a little bit, but there's a couple of, I had to remind.
This is a tour de force. And you see, this was an order of magnitude estimate that puts this whole thing into a totally different ballpark, right? Order of magnitude estimates are supposed to be simple, right?
I think the envelope, but
it's
log envelope.
And all of these somehow consider, you have to understand, see intuition, what is the right consistency condition, which are the things that should be balancing each other, and then you always get this self-consistency equation. That's what leads to these weird powers.
Let me stand up, because this is the official end of our summer school. Thanks, everybody. Thanks to all the lecturers for not giving in, even when they got on a slight detour, for showing us amazing things, how rich quantum field theory is in its applications, how rich QCD is in its very different facets, and for you guys to not run away. I believe you have learned a lot. Well, certainly I have learned a number of things, tightened down a number of screws here and there, and I think we found a couple of places where it would be a lot of fun to continue working on these things. So thanks everybody, and see you soon again, right?
I think we should also thank all of us, Heribert, for bringing us all here. It's we are very happy that you took the initiative. It's always a pleasure to be here.
Let's try to do this sort of thing again, right? Okay. Goodbye, everybody.